Space launch trajectory and countdown net. Pad is clear.
10, 9, 8.
Launch auto sequence has started.
6, 5, 4, 3, 2, 1.
Go for launch.
Vehicle is supersonic.
Stage separation confirmed. Dragon, separation confirmed. Stage 1 is transonic. Landing legs have deployed. And Falcon 9 has landed.
Good morning. It is Monday, October 7th, and on your screen is a live view of Falcon 9 as it awaits its 10:52 a.m. Eastern Time launch from Space Launch Complex 40 at Cape Canaveral Space Force Station in Florida. My name is Jesse Anderson, and I'm the Senior Engineering Manager for Falcon Structures Manufacturing here at SpaceX.
And I'm John Innsbrucker, the Falcon Principal Integration Engineer, joining you from the status desk here just behind Mission Control Hawthorne.
Welcome to our webcast coverage for Hera, the European Space Agency's mission for planetary defense, which was developed as part of a larger international effort known as the Asteroid Impact and Deflection Assessment Collaboration, or ADA. Today will mark this year's 94th launch for SpaceX and the 389th flight overall.
We're just over 19 minutes away from launch. Both the vehicle and the range are green. On the weather front, it's cloudy. It's been a little rainy. The good news right now is we think the weather will hold up and be good to go for launch when we get to T0. Now, if for any reason we have to call a hold on today's launch, a backup opportunity is available tomorrow. That's the 8th of October at 10:46 a.m. Eastern Time.
You may remember the first part of the ADA collaboration, NASA's Double Asteroid Redirection Test, or DART mission that SpaceX launched at the end of 2021, which tested a kinetic impactor technique to deflect asteroids. DART was SpaceX's first interplanetary launch for NASA and the first planetary defense test to see if humanity can change the motion of an asteroid in space. DART collided into a small asteroid moonlet called Dimorphos, which orbits around a larger asteroid called Dimorphos.
Spacecraft is on internal power.
And that happened in September of 2022, while about 11 million kilometers or 6.8 million miles from Earth. The collision shortened Dimorphos' orbit by 32 minutes, or about 26 times the predefined success threshold of 73 seconds. Hera will now return to the same binary asteroid system to survey the results of the kinetic impact up close and help researchers understand if it can become a repeatable technique among other mission objectives. Now, before we get into today's mission, here's a quick refresher on the DART mission, courtesy of NASA.
We're embarking on a new era of humankind.
Didymos and Dimorphos make a great target. We needed an asteroid with a moon that you can see from ground-based telescopes around the world.
We're doing this mission to prove that we can deflect an asteroid.
5, 4, 3, 2, 1. And liftoff of the Falcon 9 and DART on NASA's first planetary defense test to intentionally crash into an asteroid.
Even if we do everything right, our sensors work well, our spacecraft is doing well, even then, we might still miss.
4, 3, 2, 1.
For the first time ever, humanity has changed the orbit of a planetary object.
NASA confirms that DART successfully changed the targeted asteroid's trajectory.
Using the ground-based telescopes around the world to watch the system and see how it's affected by this impact event.
This is a watershed moment for planetary defense and a watershed moment for humanity.
DART changed the orbit of a celestial body for the first time in human history, demonstrating one possible capability to defend Earth from a potential future impact. Hera will visit Dimorphos to measure its mass and makeup, as well as its shifted orbit from up close, performing its own crash scene investigation of the asteroid moon. The data gathered will help validate the DART-style deflection technique for operational use in case it's ever needed to help deflect any dangerous asteroids headed for Earth. Hera is the first planetary defense mission for ESA and will be the first mission ever to perform a subsurface radar survey of an asteroid using the smallest radar instrument ever flown in space. To help complete its mission, Hera is carrying 2 shoebox-sized CubeSats with it, one called of the daughter of Hera. Hera will help pave the way for ESA's future interplanetary missions by testing deep space navigation and guidance and inter-satellite communication between the main Hera spacecraft and its CubeSats, which are packed with miniaturized technology and scientific payloads. The CubeSats will conduct proximity operations in the asteroid's extremely low gravity environment, flying lower and closer than Hera. And they will actually end their mission by landing on Dimorphos, which is 170 meters wide, or roughly the size of the Great Pyramid of Giza in Egypt. Hera is expected to arrive at Dimorphos in late 2026 to begin its 6-month investigation, delivering researchers on Earth critical data about future asteroid deflection missions and continue to grow our understanding of asteroid geophysics and build our knowledge about the formation and evolution of the solar system. With that primer, let's take a look at this video from ESA to dive deeper on today's mission and hear a special message from the ESA Director General.
There's a mystery out there in deep space, and solving it will make Earth safer. That's why the European Space Agency's Hera mission is taking shape, to go where one particular spacecraft has gone before. On the 26th of September 2022, at 6.1 kilometers per second, NASA's DART spacecraft crashed into the Dimorphos asteroid. Part of our solar system changed. The impact shrunk the orbit of the Great Pyramid-sized Dimorphos around its parent asteroid, the mountain-sized Didymos. It also sent a plume of debris thousands of kilometers across space. This grand experiment was performed to prove we could defend Earth against an incoming asteroid by striking it with a spacecraft to deflect it. DART succeeded, but that still leaves many things scientists don't know. What is the precise mass and makeup of Dimorphos? What did the impact do to the asteroid? How big is the crater left by DART's collision? Or has Dimorphos completely cracked apart, held together by its own weak gravity? That's why we're going back with ESA's Hera mission. But Hera is not going alone. It takes with it 2 briefcase-sized CubeSats to go in closer and take more risks than their parent spacecraft. And they'll end their duties by touching down on Dimorphos to gather extra data on its surface and gravity field. If a body of this size ever struck Earth, it could destroy a whole city.
I'm delighted you can join us today to watch the launch of the European Space Agency's Hera spacecraft on board a SpaceX Falcon 9 rocket. The risk of an asteroid hitting our planet affects everyone, everywhere, making planetary defense an inherently international endeavor. Hera is Europe's first planetary defense mission, which, together with NASA's DART mission, is part of the International Impact and Deflection Assessment Collaboration. In 2022, DART demonstrated that humankind is capable of redirecting an asteroid. The mission to Dimorphos and Didymos hit the smaller body and changed its orbit around the larger asteroid. Now, ESA's Hera will visit this asteroid pair to investigate how DART affected Dimorphos. Hera will gather the data we need to turn kinetic impact into a well-understood and repeatable technique on which all of us may rely one day. My thanks go to everyone who worked so hard for so long to make Hera possible. Best wishes for a successful start of this epic journey.
Launching Hera today is Falcon 9, a two-stage rocket developed and manufactured by SpaceX, known for its safe, reliable, and cost-effective access to space. Starting at the top of the vehicle is the payload fairing, a protective shell that encases the payload being sent to space. That fairing will separate and jettison away from the vehicle, exposing the payload once Falcon 9 reaches space. And here you can see on your screen a photo of Hera being encapsulated in that fairing just a few days ago. The fairing halves that we are using today have supported multiple missions, one having flown 12 missions and the other 18. Now, continuing down the vehicle, we have the second stage. The second stage is powered by a single Merlin vacuum engine, or what we call the MVAC engine, which is optimized to perform in the vacuum of space. And below that is the first stage, which contains 8 engines arranged around one center engine held in place by a structure called the octaweb. Now, each of these Merlin 1D engines delivers about 190,000 pounds of thrust at sea level, which gives Falcon 9 a combined 1.7 million pounds of thrust. The booster supporting today's mission previously launched 22 missions, including Crew 1 and Crew 2, SXM-8, CRS-23, XP, Transporter 4 and 5, Global Star FM-15, ISS Aero C-3, Korea 425, Maxar-1, ASBM, and 10 Starlink missions. Now, due to the additional performance required to deliver today's payload to an interplanetary transfer orbit, this will be the 23rd and final launch for this booster, and recovery is not planned. However, we will be recovering the fairing halves. So with that, let's check in with John I for a status update on today's launch.
The launch vehicle and spacecraft are in good health. They're ready for launch as we are just beyond T-minus 9 minutes to liftoff. The Falcon 9 team reported on console at T-minus 2 hours and 15 minutes. They began their final checks of the launch vehicle and ground systems. We did a final checkout of the flight termination system. That was at T-minus 1 hour and 45 minutes. We then had the Falcon 9 team complete their data review of first and second stage propellant checkouts, as well as the avionics team and the guidance, nav, and control team. And they did all their final data reviews at T-minus 1 hour. At that point, the chief engineer conducted a technical readiness poll, and everything was go to continue. We've also completed at T-minus 38 minutes the poll to proceed with propellant load and launch. And most recently, you might have heard over the countdown net, the spacecraft has gone on internal power at T-minus 18 minutes and 30 seconds. Now, currently, the team at Cape Canaveral Space Force Station, they are loading propellant. That began on time at T-minus 35 minutes when our launch auto sequence began. We're loading 2 propellants on Falcon 9 today, a fuel and an oxidizer. Now, for Falcon 9, our fuel is a refined form of kerosene known as RP1. To burn that fuel, we need a source of oxygen, which we call the oxidizer. Now, most burning that you're familiar with on Earth uses oxygen that makes up about 21% of the air you breathe. But in space, there's no atmosphere to provide oxygen or other oxygen-bearing molecules, so rockets need to carry their own. Now, Falcon 9's oxidizer is super chilled liquid oxygen, what we call densified LOX. Now, the liquid oxygen is chilled well below its boiling point. That allows its density to be increased, and that in turn allows us to load more into the first and second stage LOX tanks. And that's an important advantage for missions like today's, where we need as much propellant as we can carry to get to the required interplanetary transfer orbit. Now, currently on the Falcon 9, you see on your screens, fuel loading is complete on the second stage. We're continuing on the first stage up until about T-minus 6 minutes when fuel loading will wrap up on that stage. And we are loading liquid oxygen onto both the first and second stages right now. In addition to its propellants, Falcon 9 also needs an ignition source to start burning that fuel and oxidizer. And for that, we use a liquid called T-Tab.
Stage 1, RP1 load is complete.
And there we're on time. Fuel load on the first stage is complete. I mentioned T-Tab. That's an acronym for a mouthful called triethyl aluminum and triethyl borane. Now, when we ignite the engines, we first flow liquid oxygen and T-tub into the gas generator in the main combustion chambers. The T-tub will burst into flames in the presence of the oxygen. So once we have that ignition, the RP-1 kerosene fuel is introduced and the Merlin engine goes to full power. And at liftoff, Falcon 9's 2 stages that you can see next to the strongback. It's cloudy, it's been a little rainy. We started the day with a 50% probability of violating launch weather constraints. But the good news is that the weather officer forecasts that we should be go 5 minutes from now. Mostly we've been watching thick clouds, make sure they're not too cold where you might have triggered lightning. The good news is the clouds are warm. Everything looks just pretty much gloomy, a little rainy.
Tanks are pressing
with
for
that,
strongback retract.
You hear the tanks are pressing. We're getting ready for strongback retract. So inside T-minus 5 minutes, all systems are go for launch from Space Launch Complex 40 in Florida. So Jesse, let's head back and watch the last of the countdown.
Thanks, John. It is T-minus 4 minutes and 38 seconds and counting. And as John mentioned, everything continues to look go for liftoff at T0. Now,
strongback retract has started.
Perfect timing. You heard that call out that strongback retract has begun. Now what's going to happen here is the clamp arms, which are just below the fairing, are going to open up, and once those are fully open, then that strongback, or what we call the TE, or transporter erector, will begin to retract away from the vehicle. And you can see on your screen that those clamp arms are opening up there. Now, the TE is designed to transport, raise, and support Falcon 9 at the launch pad using umbilicals or flexible lines to route the vehicle's fluids, power, and telemetry from the ground systems to the rocket and the payload until Falcon 9 switches to internal power and clears the pad. And you can see the clamp arms are now fully open, and that strongback, there you can see it on your screen, the TE is now moving slowly away from the vehicle. Now this is going to recline just a few degrees here, but at T0 it's going to move even further away, about 45 degrees away from the vehicle as Falcon 9 lifts off. And there you can see that the TE is pretty much fully reclined there on your screen.
Coming up on T-minus 3 minutes. Strongback is in the countdown configuration. It's about 1.5 degrees away from the Falcon 9. Waiting for next is completion of liquid oxygen loading on the first stage.
Stage 1 LOX load is complete.
Right on time. So at this point in the countdown, the first and second stages are nearly fully loaded with the 1.1 million pounds of fuel and liquid oxygen. We have loaded all of the fuel on first and second stage. Liquid oxygen is now complete on the first stage. The last major event will be T-minus 2 minutes when we finish loading liquid oxygen on the second stage. And you can see right there the cold, chilled skin of the second stage is the warm Florida air moving by it. We're seeing the condensation of the moisture in the air. Everything continuing to look good as we come up on T-minus 2 minutes.
Stage 2 LOX load is complete.
And there's that call out that liquid oxygen loading is now complete on the second stage. Now that means that propellant loading is complete on Falcon 9. And that's over 1.1 million pounds of propellants now loaded on the vehicle. All systems remain go for launch. SpaceX ground computers are now draining propellant out of the lines that go up to the strongback onto the second stage. And there you can see that venting happening there on your screen. Now this creates a white cloud, which is pressure from the ultra-cold liquid oxygen line that's being vented there.
Front gas closeouts.
Again, when that cold liquid oxygen gas meets the warmer ambient air there, it creates that condensation that you can see there on your screen. The first and second stage computers on Falcon 9 will execute stored programs to prepare the rocket for flight, leading to the ignition of the M1D engines at T-minus 2 seconds and liftoff at T-minus 0.
Falcon 9 is in startup.
With that call out, the Falcon computers are running the final sequence for launch. First and second stage tanks are beginning final pressurization for launch. All systems are go. Let's listen in to terminal count.
LD, go for launch.
As Falcon 9 transports the European Space Agency's Hera spacecraft into space.
.30 seconds. Seconds. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition, engines full power, and liftoff. Go Hera, go Falcon, go SpaceX.
Vehicle is pitching downrange.
Stage 1 propulsion is nominal.
At T plus 30 seconds and counting, Falcon 9 has successfully lifted off from Slick 40. After clearing the tower, we begin to tilt or gimbal the engines. That initiates a roll maneuver you might see on the Stage 1 camera view, although it's kind of cloudy. But this enables the vehicle's antennas to stay in the best position for communicating with the ground. We are into throttle down now in preparation for max dynamic aero.
Falcon is supersonic.
Faster than a speeding bullet, we're supersonic on Falcon 9. Waiting for the call out from GNC of Max Q.
Max Q.
Right on time. We're through the period of maximum pressure on the vehicle. The Merlin engines are back at power, and we're out of the throttle bucket. Now, from here on, even though the velocity is rapidly increasing, the atmospheric density is decreasing, and that's resulting on less loads on the Falcon 9. 90 seconds into flight, the rocket typically needs to go 17,500 miles per hour horizontally in order to avoid gravity pulling it back down to Earth and getting into orbit. We've heard the call out for MVAC chill. That's a bleed valve on the second stage engine. That's performing the final chill prior to second stage engine ignition. All's looking good with the first stage trajectory. We're coming up on T plus 2 minutes. Views from onboard the camera mounted on the inner stage of Booster 1061. Now we've got 3 events that'll be coming up in just under 30 seconds. Main engine cutoff, the 9 Merlin engines will be throttled down and shut down. Then we'll get stage separation and then startup of the MVAC engine on its first of 2 burns on the second stage. We've begun throttling down the Merlin engines.
Main engine cutoff.
Call for MECO.
Stage separation.
Successful stage separation.
MVAC ignition.
MVAC ignition and westbound power on stage 2. Coming up will be fairing deployment. And for the first stage, as we saw it in the background, farewell 1061, and we thank you. As we continue climbing out of Earth's atmosphere, we're waiting for the right time when we can open up and deploy the fairing. That should be coming up in about 10 seconds. There's a camera view as we switch. You can see Hera inside the 2 halves of the fairing.
Fairing separation.
and successful payload fairing separation. As we mentioned earlier, the fairing halves have supported multiple missions. One half has flown 12, now 13 missions, and the other had previously flown 18. And those fairing halves will come back down to Earth. They're guided by cold gas thrusters and then parachutes or parafoils.
Falcon is on a nominal trajectory.
They'll deploy and they'll be recovered by our recovery vessel, Doug. Jesse, T plus 4 minutes, 23 seconds. Everything continues to look good on Falcon 9 with Hera.
Thanks, John. Yeah, everything's looking great. We got some awesome views here on your screen. What you're looking at is a view of the MVAC engine on the second stage with a beautiful view of Earth in the background.
STS has safed.
Now, we are currently in the first of 2 planned MVAC burns for this spacecraft. And we have separated for the first stage from the first stage. As we mentioned earlier, we will not be recovering the booster as we usually do. Now, typically we would land the booster either on a drone ship or back on land, but due to the performance, the additional performance required to deliver this payload to an interplanetary transfer orbit, we will be not recovering the booster today. Now what you are seeing, again, is the MVAC engine. The MVAC engine is optimized for the vacuum of space and has about 220,000 pounds of thrust in vacuum. Again, this is the first of 2 burns. The 2 burns for the MVAC engine will take the second stage with the payload attached to the targeted drop-off orbit.
Falcon continues to follow a nominal trajectory.
And great call out there, following a nominal trajectory. You can also follow along with the speed of the vehicle as well as the altitude in the bottom right-hand corner of the screen. And the next event coming up in about a minute and a half from now is SECO 1. SECO 1 is second stage engine cutoff 1, which is where we will shut down that MVAC engine and allow the vehicle to coast with the payload in an Earth orbit, and then we'll reignite that MVAC engine for a second time to take the vehicle and payload to that interplanetary transfer orbit. Now we're just about a minute away from SECO 1. And you can see in the bottom right hand of your screen that the speed is continuing to pick up. The velocity is increasing on the vehicle as the MVAC engine continues to burn. But again, in about 40 seconds from now.
Stage 2 is in terminal guidance.
In about 35 seconds from now, we will shut down that MVAC engine and again allow the vehicle to coast in an Earth orbit before we make its way to the interplanetary transfer orbit.
Stage 2, STS has safed.
Continuing to get good callouts and some great views here. Again, this is from the second stage looking at the MVAC engine. The Hera payload is still attached.
MVAC shut down.
Nominal park orbit insertion.
And great news. We heard the callouts as well as saw that MVAC engine shut down, and we got a good confirmation of nominal orbital insertion. Now, the second stage is now embarking on the first portion of its coast phase. Coasting in this orbit will last about 45 minutes, and we will light that MVAC engine for a second time around T plus 52 minutes. So we're going to take a pause, and we'll see you back here at T plus 52 minutes for SES-2.